welcome to Technical Tuesdays. We're going to have a look at our rope rescue equipment, just a quick overview of some of our key equipment. We're going to be looking at our harnesses, we're going to be looking at hardware and software, so our ropes, carabiners, pulleys. We're going to look at the properties around them and how we care for and identify them. For equipment, the standards we're looking at, we have two main standards directly related to equipment, and that's the NFPA 1983. NFPA 1983 is designed for the manufacturer. It tells them how they're going to manufacture equipment, how they're going to test the equipment, what strength requirements that they have to meet. NFPA 1858 is a newer document, came out in 2018. This document is directly related to us. In the past, we had trouble relating to documents directly to the fire service. This tells us now how we are to track, maintain our own equipment, and care for our own equipment. So this is an important and new document for us. Okay, NFPA classifies our gear into two main classifications. One is G, general use, or T, technical use. G rating has the higher strength rating, and then T has a lower strength rating. Why would we ever use T? Well, it's lighter, so teams that are really concerned with weight are going to use T-rated equipment, technical use, and it also requires a higher knowledge requirement to use that equipment because we have to be able to do the math and determine if we can still meet our safety factors with gear that isn't as strong to begin with. We use kilonewtons a lot when we talk about strength requirements for rope rescue. And 1 kilonewton is roughly 225 pounds, or 224.8 pounds to be exact. That's an important thing when we start to look at strength requirements and system safety factors. Also, we measure our rope in meters and also in millimeters. So the diameter of our rope, for example, we use 12.5 mil rope as our life safety rope. This is just a quick conversion table showing conversion. We won't get into it between kilograms and pounds for us and kilonewtons, but we're going to look at software. Again, we're classifying our gear into hardware, which is anything hard, and then software. Software is anything soft. NFPA defines it as a type of auxiliary equipment that includes, but not limited to, anchor straps, pickoff straps, and rigging. So anything that's software, anything that bends, anything made out of nylon, polyester, that's our software. Nylon. Nylon is one of the key fabrics used in rope rescue. It has been used for years. It's used in many things in the industry. We're going to look at the melting strength. So melting strength here we're saying is 480. Be aware there is a variance. So if you Google melting strength of nylon, you may get it in. If you look at our different manuals, there may be different things. When we took this number, specifically took it, we want to prepare ourselves for, in the eventuality we may get to write an NFPA exam on this and get certified. We don't know when or if that'll ever happen, but taken from this book, it's 480 degrees Fahrenheit. Also, it loses 23% of its strength. Again, that number can vary to a degree, but again, we're using this resource, and 23% of its strength when it's wet. So that is a key factor to understand, that especially if we go to consider system safety factors. Now we have to look at, this is pouring outside and our ropes are actually having a further reduction. Polyester. Polyester is another key fabric with rope rescue. Our ropes are actually manufactured out of polyester. We have Sterling HTP, or high tenacity polyester ropes. Again, it does have a higher resistance to UV, it has less stretch, so it's more static even than a nylon rope would be. And it also has minimal strength loss when wet, so we don't even account for strength loss when polyester is wet. So that's a key factor as well for us. We don't have to worry about our rope losing strength when wet. You may ask, why not Kevlar? Why don't we use Kevlar for our ropes? This is one of those things that it is extremely strong, but it's not good with abrasion, and it's not good when it gets bent. So it loses a lot of strength when it gets bent because we knot our equipment and not our ropes. It is not a good choice for rope rescue. Rope construction. Our ropes are constructed as Kern mantle. Again, Kern being the core, mantle being the sheath. 75 to 85% of that strength, where again, numbers vary, but we're using this as our guide. 75 to 80% of the strength is in that core. So the sheath has some of the strength, and its main job is to protect that core, that kern. The next, our ropes are constructed with a block creel construction. That means that the fibers run continuously from one end to the other. They're not broken. They're not spliced together. If it's a 30 meter or 100 foot rope, that fiber on the inside runs, each fiber is a full distance, that full length construction. Our Sterling rope. So our rope that we're currently using in BFES is made by Sterling. It's a G-rated rope, so that's meets a 9,000 minimum breaking strength requirement. Keep in mind, of course, when we put a knot in rope, we reduce its strength. It has a 7% elongation, with loaded at 10% of its minimum breaking strength. Next thing to note about our rope, service life. NFPA 1858 states that our software has to be expired 10 years after the date of manufacture. However, our rope, manufacturer Sterling, has a more stringent requirement, and this again is for our rope only, the Sterling rope. It requires that we retire a rope after 5 years of being in service. So the rope could potentially sit on the shelf for several years, up to 5 years, and then it could go into service on the truck for another 5 years, but it has a maximum of 5 years service life. Be aware that NFPA 1983 says that life safety rope will have a elongation of between 1 and 10% at 10% of its minimum breaking strength. Our Sterling rope, remember, has a elongation of 7% at 10% of its minimum breaking strength, so it falls within that category. Care and maintenance. A lot rides on the line for our rope. Our lives are riding on the line. It's very important that we maintain our rope in good working condition. In order to do that, after each use, we have to inspect it. We have inspection logs, and those logs are kept. We have a sheet for every single life safety rope that we have, and those are kept in the drawer in the back of the squad. If a rope fails inspection for whatever reason, then it is to be tagged with an out-of-service tag, put in the cage, and then the rope STI and leads are to be notified. Rope identification. It's very important that we identify that we're using the proper rope for the proper job. We had an issue years ago where we had some water rope, and it was purchased and it looked almost the same, almost identical to our life safety rope. A bag of it also ended up on the squad, and it was the same diameter, and it also had a tracer. But the problem is it has a much lower breaking strength. So what we've done to rectify the problem, we have a couple main ways of recognizing a life safety rope. One is it has to have a tracer through it. So on the top right, you're going to see the life safety rope, and it has tracers running through it, that spiraling of the different colored threads around the rope. That indicates that it's a life safety rope here at BFES. On the other hand, you'll see in the bottom right, the rope is solid. It's a solid red and it's a solid orange with no tracer. That indicates that it is not life safety for high angle rope rescue. So that is a first quick visual indicator. The next thing we have to identify ropes is the tags. Looking closer at the tag, you'll see that the first 3 characters are letters. In this case, it's RES, which stands for rescue. The next 2 things we see is a number. That number signifies the length of the rope, in meters in this case. So it's a 90-meter rope, or roughly 150 feet. The next 3 digits are our internal rope number. So each number, it gets, before it's put in service, gets logged in our master inventory, and it's given a unique identifier number so we can identify it and track it. And then the last digits, the last group of digits, in this case 10, 15, are when it goes in service. So that tells us, again, how long it's been in service. In this case, it went into service in October 2015. And another example, what is this rope used for? In this case, starting with a W, water rope. 60 meters, and it was put into service December 2013. So knowing a little bit of our labels helps us understand exactly what rope we're using. Prusiks. Our prusiks are made out of what we call cordage. It's 8mm cordage. They have to be a smaller diameter so that they'll grip the rope properly. Our prusiks have a minimum breaking strength pulled end to end of 3,500 pounds. And we construct our prusiks into 2 different sizes, a larger size and a smaller size, so that they can be used in tandem. We use mostly all tubular webbing. Tubular webbing industry-wide has a minimum breaking strength of 4,000 pounds. Flat webbing also exists in the industry. It has a minimum breaking strength of 6,000 pounds. As we look at the construction of the webbing, just quickly, there are 2 main constructions of webbing: needle loom and shuttle loom. Shuttle loom webbing ends up being constructed in a circular pattern, so it's actually weaved in that tubular shape. Needle loom creates it in a flat, so it'd be manufactured as a 2-inch wide web, folded over, and then stitched along the edge. In a perfect world, we'd be able to get shuttle loom webbing because it's a continuous. It doesn't have a weak spot. It doesn't have an edge stitch to it. However, the reality of modern manufacturing is it's much more economical to do needle loom webbing, and it's kind of the reality of modern manufacturing. So we do have it. It's not an issue for us. We purchase from reputable manufacturers, but just be aware there are 2 types of manufacturing methods for it. When we look at our harnesses, important to know, as rescuers, we understand that you may be thinking, why do I need to know what types of class of harnesses there are? Because I'm just going to use whatever's there for me. As rescuers, as we become competent rescuers, it's a knowledge component. We need to know that there are different classes and what they're for. Class 1 harness is simply a seat harness. It's a lightweight seat harness. So it really is not used for rescue for the majority. And in fact, NFPA 1858 recognizes only Class 2 and Class 3 harnesses as rescue harnesses. So when we look at Class 2, a Class 2 is simply a seat harness as well, but it's beefier. It's a heavy-duty seat harness. It's designed to actually be able to do rescues with. In Class 3, which is what we have, is a full body, includes a chest harness and a seat harness built in together. So we use a Class 3 harness. Life safety harnesses, we're going to continue on with the connection points. Very important that we understand the connection points and what to call them. It allows us to communicate where we're connecting to and also understand what they're designed for. So some of them have very different purposes and functions and limitations. We're going to start with our ventral connection point. This is generally our main connection point for our main line, and that's on the front of the waist. That's our ventral. Next one we'll look at is our sternal connection point. Our sternal connection point is often used for belays, and also if we're using, for example, Y-lanyards or anything that has a shock absorbing function in it, it can head to our sternal because our sternal has an arrest rating. You'll see the A on beside the rating. That has an arrest rating, meaning it can be used as with a fall arrest type system. And the next one would be our dorsal connection. Our dorsal connection is the other one that has a fall arrest rating. Now, keep in mind, we want to look at the difference between those 2. Advantages and disadvantages. Our sternal connection, if we end up getting suspended by our sternal connection, that connection puts us in a fairly good position. It allows us to self-rescue fairly easily. We can reach the rope. We can get ourselves out of that position. It also keeps our weight in the harness designed as the way it's designed to be. It keeps us more in an upright seated position. If we use our dorsal and we get loaded in our dorsal position, it puts us in an extreme forward position, and it puts us in a position where we're a very difficult position to self-rescue. The harness starts to dig in. Our shoulder straps dig in severely into our neck, becomes extremely uncomfortable. Also, the leg straps dig in a way that they're not designed to dig in, and they start to cut off circulation. It can fairly quickly lead to orthostatic intolerance, a life-threatening situation. So, depends on the situation. The other disadvantage with the dorsal is if we're rappelling down against a wall face and all of a sudden a mainline failure and we get loaded abruptly from the dorsal, it's going to throw us forward, potentially slamming ourselves into the wall face first. Using the sternal overcomes a lot of those challenges. The disadvantage is it puts now a rope in front of us in our working area. So we're now having to work around this rope. But in a lot of cases it can be advantageous. So it's important to know the differences between those when we make our selection, where we're connecting to our sternal or dorsal. Our side attachment rings, you can barely see them in the picture, the metal rings connected to the side, those are designed for work positioning. So they're not a main connection to be hanging from. They can be used as work positioning with a buck strap from side to side to hold us into a structure while we're doing our rigging or operating a piece of equipment. Some of our harnesses also have a connection on the very back of the waist. That is to be used for a travel restraint only. That's only to limit our travel towards an edge. Okay, we're going to look at hardware. Again, we have hardware and software. We're looking at hardware. Hardware is defined as non-fabric components of protective clothing or equipment, including but not limited to those made of metal and plastic. So anything metal or plastic is considered by NFPA 1858 and 1983 as hardware. As such, it has to have certain markings on it. So it has to be stamped with the, if it is NFPA rated, it has to be stamped, permanently marked with that minimum braking strength rating, or whether it's a G or a T rating. Examples include carabiners, pulleys, bar racks, and lots of other things. Metals. We have two main materials that our hardware is made out of, so we have steel and aluminum. The advantage of steel is it's stronger. The advantage of aluminum, pretty simply, is that it is lighter. Descent control devices. We have several options for descent control devices on our department. We're going to start with looking at the bar rack. So the bar rack is kind of the old standby. It's what we used to use for rappelling all the time. It's still in our JPR kits and will remain in our JPR kits. Big advantage is it does really well with dirty ropes. It can handle dirt going through them, hence why they're going to stay in our JPR kits. If the ropes are in dirt and traveling through, it does great. Also, the friction can be varied under load. So if we lower a rescuer down, or if we rappel down and all of a sudden we pick off somebody, now we're doubling our load potentially, significantly increasing our load. A bar rack allows us to vary that friction while the device is under load, which is an important feature. The next piece we'll look at, which is rarely used, is a tuber brake. We do still have one, and it does, again, it will handle wet, dirty ropes well. It will also allow a knot pass, which is a unique feature with the descent control device. It's the only one that we have that allows a knot to actually pass right through the device. The next one we'll look at is the ID, Petzl ID. The red ones are rated for rescue. They allow us to actually have a two-person load on them. They are extremely useful as a descent control device. They are our number one choice. For a descent control device currently, they're small, they're versatile, they're safe, they lock off, and they're just very easy. They were modified from industry. They use them in industry for those exact reasons. They're very versatile and functional, and they just beef them up for rescue. They also can be modified while under load. We modify them slightly to be able to sufficiently handle a two-person load. The next one is the MPD, or multi-purpose device. That device, while it can be used on your person as a rappel or descent control device, it shines up top. It's bulkier, but up top, say if we're lowering somebody, it shines at the top, and it can be quickly and easy converted from a lower to a haul. It eliminates almost any sort of hiccups with conversion. So it's an incredible device. It shines up on the ledge instead of as a rappel device. Carabiners. We have both aluminum and steel carabiners. We are seeing a gradual change in the industry, and you will likely see us changing gradually to G-rated aluminum carabiners. Historically, steel was the only G-rated carabiner you could get. There is a gradual transition in the industry, and we're also likely going to see that change here at BFES. We also have some screw lock and some auto lock. Remember that auto lock carabiners also have to be checked to ensure they are locked by pushing the gate, because there are gates can wear out and malfunction and not close properly. Parts of a carabiner. It's important that we understand the parts of the carabiner for practical purposes as well, so we understand how they work and also how they can and cannot be loaded. When we look at the carabiner, the strongest part of the carabiner is the spine, and the spine being on the opposite side of the collar. So it's the side that has no collar, and it is the strongest point. That's where it's designed to be loaded closest to. Next, as we work around the carabiner, we get around to the gated side, and we have the nose that leads into the gate. So then on the end of the gate, we have the collar that locks it closed. On the very end of the nose, we have a slot and a latch, and that slot allows the hinge pin to make a mechanical connection into that nose. We then, as we travel down that gate, we then have the hinge at the bottom. Keep in mind there's a hinge pin and there's a latch pin. Those pins are one of the weakest links on a carabiner. So that's something to keep in mind as far as when we do our inspections. We want to make sure those hinge pins and that latch pin are in good condition. The other thing we want to look at and be aware of is the shape of carabiners. There's a number of different shapes of carabiners, but you'll see the two diagrams with the dotted line running through them. We'll talk about the oval first. The oval, that dotted line represents where that load is going to settle and pull through. You can see the oval pushes the load to settle in the middle of that upper arc and that lower arc. That means that some of that load, or half of that load, is going to be transferred over to the gated side and land on those pins and everything as well. And remember that gated side is weaker. So that's where, when we look at a D-shaped carabiner, that D shape forces that load over to that long axis, which is the strongest part. So therefore, the D-shaped carabiner is the strongest shape of carabiner that we can get. And you'll see that I want to say all of our carabiners are a D-shaped carabiner, and that's why the D-shaped carabiner is as strong as it is, because the load is mostly all transferred to that long axis. Pulley components. Again, important that we understand our equipment and what it's made up of and the components of it. Start by looking at the side plates. The side plates are the housing that the wheels are inside, that houses the whole thing in. The next thing we'll look at are the sheaves, or the actual wheel. The sheave is the grooved wheel that the rope rides on. The next thing we have is the axle, and that's the pin that runs through and the wheel turns on. And finally, on double pulleys, we have what's called a becket, which we'll look at a little bit more in the next slide. But that's where, on the very bottom of that double pulley, you'll see that becket extending down below. That has a hole in it designed for a carabiner to go through that allows additional carabiners to be attached into it. Whether we want to attach another pulley to the bottom of it or terminate a rope end on that, that becket allows us to terminate that rope end. Pulley size is determined by the diameter of the sheave. So it's one of those things we look at. A lot of our pulleys are at least 2 inches, which meets our 4-to-1 rule with our rope. So the sheave is traveling around something that's 4 times the diameter at least of the rope. Some of our pulleys are smaller, but just something to be aware of. Diameter of the sheave, it determines the size of the pulley. Here we get a better look at those beckets on the bottom, where we can connect another carabiner and make additional connection points. Also, we see a prusik minding pulley with the shoulders on it, the red one with the shoulders. It is designed to work with a prusik and actually mind the prusik as the rope travels in. It stops the prusik from traveling into and getting jammed in the pulley. The double pulleys, you see one of them, the silver one, is not a prusik minding pulley, so it is not designed to be used with prusiks coming into it. And the red one is a prusik minding pulley, and it is a double, so we have those as well. And we also have a Omni block. That Omni block has a small shoulder on it, only on one side. So it is a prusik minding pulley, but it has to be used with the prusiks on that shoulder side. So it takes a little bit of awareness to know that prusiks can be used, but only on that shoulder side of the pulley. Additional hardware. Some of the additional hardware we have at Barrie Fire are, we'll start with the Kootenay carriage, that large carriage pulley. It's commonly used, it's very strong, and it can be used in high lines, and it can also be used as the actual carriage pulley for that the load runs across. Other advantage of that pulley is it can actually pass a knot through it. So the only pulley we have that a knot could actually ride right through the pulley. Next we have anchor plates. Common connection point for a lot of our rigging, if we're rigging more than one thing on an anchor system. Next is an anchor ring. Again, an anchor ring is extremely strong, and it can be used as a collection point for rigging if we wanted to. Next we have a hand ascender. Hand ascenders, keep in mind, have a limitation. They have extremely aggressive teeth on them, which are known to de-sheath ropes at higher loads. So they're commonly used for ascending, for personal use to ascend a rope. Where we want to avoid using them is in haul systems. So we can generate higher amounts of force in haul systems. So we want to keep them away from that high tension environments. The next, we have a rescue sender in the bottom middle, and that's designed, it's a mechanical rope grab as well, but it's designed with ribs and much less aggressive teeth. That ascender can be used in haul systems. It doesn't have the same de-sheathing effect on the rope as the aggressive teeth in the hand ascender. And finally, we have this swivel, which can be used anywhere in our systems, anywhere where we're going to have potentially spinning, any type of spinning in the system, and we want to eliminate that twisting. Edge protection. We're going to look at the types of edge protection that we have here at BFES. Edge protection is extremely important. We have to protect our rope from any sharp edges. Edge protection or lack of edge protection, abrasion, accounts for up to 90% of rope failures. So it is extremely important. We classify it into 2 different types. So we have dynamic, which allows a traveling rope to run over it. So we're going to have a rope actually running. If we're lowering somebody, or the belay rope is running over it, it's a traveling rope, and it requires a dynamic type of edge protection. So for those, we have our CMC Ultra Pro, which is the plastic white one. It will actually allow dynamic. It's designed for ropes to run over it and run through it. Next, we have the stainless steel one, Born Entry Ease, which is an excellent option for dynamic ropes running over it. It is heavier, but it stays in place really well. It's an excellent option. And the last one is edge rollers. So again, it will allow ropes to travel up and over the edge, and really helps us reduce the friction of that edge as well. The next is static. So static edge protection are things like, you'll see our tarps, our rope sleeves, and even old carpet from probably the 1960s that we have a BFES. Now it is designed for ropes to only rest on top of them. So if we're going to rappel down and that rope is not actually traveling over it, it's just resting on it, those types of edge protection are excellent. Equipment strength. We're not going to go extremely deep into equipment strength, but we have to understand equipment strength so that we can make appropriate selections and choices when we choose equipment and put it in the right locations. And we also need to be able to figure out what our system safety factor is. So we need to be able to identify the weakest link in our system and then figure out what our load is and determine our system safety factor as a result. So the only thing we want to look at for right now is the general use life safety rope. I want you to remember, general use life safety rope has a 40 kilonewton minimum breaking strength, or 9,000 pounds. And the other one I want you to draw your attention to is a general use carabiners. Again, same rating. It's got a 40 kilonewton or 9,000 pound breaking strength. For now, it's important that we understand and remember those two strengths. To summarize, we covered a fair bit of things. Life safety rope is constructed as kern mantle rope, and it is a block and creel construction. It has those continuous fibers from end to end. NFPA organizes gear into hardware and software, two main categories. It also recognizes general use and technical use ratings. 1 kilonewton equals approximately 225 pounds or 224.8 pounds. Although nylon rope fiber, has been the fiber of choice for many years, there is a swing to be using more polyester. So we are, on BFES, our ropes are polyester. Our webbing and other straps are nylon still. Well, nylon rope loses approximately 23% when wet. Polyester rope has minimal strength loss when wet, and we don't consider it. Aluminum and steel are the two primary metals that make up our hardware. Pulleys are made up of side plates, the sheaves, the wheels, which are the wheels, and the axle, and there's an axle bearing as well, and the becket on the bottom. Thanks for joining us for Technical Tuesdays.